Hello, IGCSEs. Hello. This is basically the last waves lesson, right? It's our third module. So we're doing 8 modules in total. We're coming to the end of the third one. We've got one more lesson until the summer holidays next week. I'm going to do a bit of mopping up and a big test for you. Well, like a quiz. It's just a quiz. So this lesson, it's on signals. I have to be perfectly honest with you. You know there's 2 specifications. So Edexcel Pearson can write your exam, or Cambridge can write your exam. Edexcel Pearson don't actually need you to know anything about signals. Yeah, sorry. So if you're sure that that's the exam that you're doing, you don't need to be here, but you should be here anyway because information is fun. This is all Cambridge. Next week, very quickly, we'll go through the Doppler effect, which is just Edexcel. Okay, so on that motivating note, let's talk about the difference between analog and digital signals. In fact, I will just tell you, and then I'll give you examples. An analog signal is a continuous signal, and a digital signal only has certain values, like 2 values. So for example, a classic example is a thermometer. This is my gorgeous diagram of an analog thermometer. Let's say that this is 2 here, and this is 3, all right? So you could read the thermometer and say the temperature is, maybe you'd say like, well, it's just past 2.5, isn't it? So you might say 2.6. But if you zoomed in, you might find that it's actually between 2.6 and 2.7, like 2.65. And if you zoomed in even more, you could get an even more precise measurement. Do you see what I mean? It's just a continuous, like down to an atomic level. There's really an infinite amount of measurements that you can have of temperature. Whereas a digital thermometer, like this one, which is super low on battery, but I think it'll just about, there we go. The digital thermometer is just giving a reading of 37 degrees, and that's it. It's just a value. I mean, obviously, some people were saying on Facebook this morning that you can get like decimal places. You could get a digital thermometer that measured in like nano degrees, but it would still, you wouldn't be able to zoom in, and there would come a point where it would stop. So the clock is the other classic example. This is an analog clock, right? So at the moment it's, oh, how jolly awkward. It's 7 minutes past 2, right? But we've got this second hand here, which is continuously moving. So we can see that it's halfway between 7 minutes past 2 and 8 minutes past 2. Whereas a digital clock, which I've got, I'll just be lazy and show you it on the corner of the screen. I'm sure you've got a digital clock nearby if you're using something digital. A digital clock only, we don't know how close this is to 8 minutes past 2, right? It's just showing us the minutes. And again, you can get digital clocks with seconds, but my point is, analog signals are continuous. So like my voice is an analog signal, okay? We've talked about this before. My voice box is vibrating, and it's doing a completely different level arrangement of frequencies and completely different amplitudes, right? So let's get rid of this. Let's start talking about signals. That's one border of it. You can tell it's nearly half term. Everything's scattered around. So we've looked at how if you put a voice signal into a oscilloscope, you can get something like this, right? Constantly changing. A digital signal is different. Yeah, I'll tell you. Well, let's go to the PowerPoint. So an analog signal, analog data, I've put information, data is really the best word. It's continuously changing. Any value is allowed, but computers can't process that. They've got to use digital signals. What is a digital signal? Well, in everyday, real, non-computer life, we use the decimal system, right? You're familiar with this. There are 10 possible numbers, and we use them in different combinations to mean different things. You know, the decimal system. This is actually, if you've never thought about it, really weird. So there are only 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It feels like there should be more, but that's all we need, right? To describe everything in our lives. Because obviously a 10 is just a 1 and a 0 together. So that's the decimal system that we're all familiar with. Computers use the binary system. There's only 2 numbers that computers use. A 0 and a 1. So how you are hearing this video is my voice, an analog signal. It's going into my phone, and we will do electromagnetism later, which will make more sense of this. But very basically, my phone or computer converts this analog signal into, it's a voltage actually. And what the phone on the computer does is it says that anything above a certain voltage is on and anything below a certain voltage is off. Anything above a certain voltage it will call a 1, and anything below a certain voltage it will call a 0. And it just turns those vibrations of my voice into a voltage which just gets turned into a bunch of ones or zeros. So for example, like if this is voltage here, then it's usually 5. If there's 5 volts, then that would look like this. If it was a digital signal, that would just be on, or yeah, that would be a 1 being sent. And if there was a voltage lower than 5, then that would just be off. You don't get this continuously changing data. It's just, is it on or is it off? And again, this is 0 volts, but there's a bit of flexibility. Like if it picks up 0.5 volts, it's just going to say, oh, we'll call that 0. And if it picks up 4.7 volts, it'll call that 1. So a graph of a digital signal would look like that, as opposed to the ones that we've been looking at a lot, analog signals, sort of look something like that. Okay, right, so let's talk about bits very briefly. What is a bit? What's a byte? Well, one binary number is called a bit. It's just the smallest unit of data that there is. So a 0 travelling through my phone is a 1 bit. It's the smallest unit of data that you can get, and a byte, which you've probably heard of, is 8 bits. A megabyte is, right, let's careful, that's 3 numbers, and that's 3 numbers. So how are we going to say that number? That's 1,000, and that's 1,000, right? So it's 1,048,576 bytes. You don't need to remember that. The nice way to think of it is picture these little transistors, tiny little switches in computers. They've got billions of them, and they can just be on or off. So in binary, if the transistor is off, that's a 0, and if it's on, then that's a 1. Okay, right. I think you're ready for my big sheet of graphs. Here we go. Which of these could be a digital signal? Explain your answer. We've got A, B, C, D, E, or F. This is supposed to be sort of quite hard. I haven't given you that much information, but I'm thinking this will be a good way for you to work out how much you've understood. And hopefully if you get a question wrong now, you won't get it wrong at the exam. That's usually the way it goes, right? So have a look at these 6 graphs. Which one of them could be a digital signal? I haven't told you how many digital signals there are here. So A is just a kind of wiggly line like we're used to drawing with waves. B is kind of the same shape as that wiggly line, but they're straight lines. It's almost like just a bunch of triangles in a row. C, it just goes straight across and then straight down to 0, and then across on the 0, and then straight up and then straight across again. And they're all the same height. So you basically just got 4 little squares in a row. D, it's the same, but you've got 4 rectangles in a row. E goes below the 0 line. So it goes like straight and then right down, but past 0 to say like -1, and then across. And just keeps repeating. And F, again, looks like a kind of angular snake. It's a lot of pyramids, but they're all along the 0 line. Which of those could be digital? I'm so kind, aren't I? The way I pour coffee on purpose just to give you thinking time. Are you ready? They were doing obnoxiously well on Facebook with this morning. I was hoping that I would catch them out. So A, that is continuously changing, isn't it? Up and down, there's all kinds of different values in there. So that is definitely not a digital signal. B, well, the lines are straight, but that's definitely not a digital signal. That's still continuously changing. Remember, digital signal can only be on or off. So C is a digital signal. That is just a reading of on. We haven't put any numbers along the side here, so it doesn't really matter what they are. It's on or it's off. It's on or it's off. So yeah, that's a digital signal. D is the same. It's on or it's off. Digital signals only have 2 values. So C and D, that's good. E, I was hoping that I'd catch you out with E. This is not a digital signal because they can only be on or off. Digital signals can't be negative. So this going below the 0 line here, That is not a digital signal. They might try and catch you out with that. And F, hopefully you've worked out that no, this is not a digital signal because it's more than one value. Okay, if you think you got it, have a look at this then. Is this a digital signal? Based on what I've just told you, is this a digital signal? 6 seconds, just a yes or no, innit? So this time we've got the columns, if you like, are different widths. But it is a digital signal, yeah, because it's only got 2 values. It's only got whatever this is and 0, and it's not negative. So yeah, we could comfortably say that is a digital signal. All right, let's talk a little bit about bandwidth. All these words that you probably heard of, but maybe you didn't know what they were. Bandwidth is the maximum amount of data that can travel in a given time. The maximum amount of data that can travel in a given time. I'm going to be really mean here. I'm going to see how much you remember about data. It's measured in, you tell me. It's one of these. So bandwidth, it's like, you can use data and information interchangeably, but strictly speaking, it's data. The maximum amount of data, information you can send in a given time, that's called your bandwidth. What's it measured in? Is it miles per hour, words per second, digits per meter, bits per hour, digits per second, bits per second, or meters per second? Which one? Again, this is 5 seconds. It's bits per second. Well done if you got that. It's not, because a bit is tiny. A bit is so tiny it's pointless. So it's megabits per second, Mbps, or it could be gigabits per second. So I've put gigabits. It's gigabits per second, GBBS. Not to be confused with megabytes, which is used to measure file sizes. So this is something that comes up a lot in past GCSE questions. If you increase the bandwidth, that is a good way of increasing the amount of information that a digital wave can carry. So you quite often get asked, how do you increase the amount of information that a digital wave can carry? That's a good one. Increase your bandwidth. Right. What you can do is quite easy to check your own internet speed. So that's what I'm going to do. See how many megabits are being downloaded and uploaded. So I've literally just put internet speed test into the internet, and I'm just going to click. In fact, I'll do it in front of you to make it more interesting. Yeah, I won't say anything yet. I'll just do it. Here we go. So I've literally just typed, what's my internet speed? And I will run my speed test now. And there we go. Whoa, look at that. So there's the megabits per second. First of all, it's testing the speed that it can download things. Oh, this is interesting. And now it's testing the upload. Huh. There we go. Your internet connection is very fast. Now, the interesting thing is I did that on Facebook this morning because we've been having real problems with Facebook being really sticky, and I wanted to show them that it wasn't my internet that was the problem. And actually, it came up with a completely different value, and I don't know enough about it, but I'm wondering if... So you have like a certain bandwidth, say this house has a certain bandwidth that it can send and receive, and all the devices have to share that bandwidth, right? So the bandwidth, like the bits per second, megabits per second, that my computer can use is different when I've got my phone on as well, because suddenly they have to share. And if my husband upstairs in his office starts doing loads of stuff, then he has to share that as well. And you would expect maybe the internet to slow down, like because each one of us is using a narrow bandwidth. But yeah, on my phone on YouTube, it didn't seem to be the same. Anyway, this is very boring for everyone except me, so let's move on. I don't usually do this. This is just a game called How to Get Marks at GCSE without actually learning anything. How to increase the amount of information a digital wave can carry. One of the ways you can increase the bandwidth. You could also increase the bit rate. Hopefully that's fairly self-explanatory. You could send more bits or more pulses per second. And you can also do something called adding another level. in the homework PDF that I always make for you, I'm going to try and add lots of resources so you can do lots of reading around this in your own time. Because, yeah, you can sort of add another level, but you end up with graphs that look like this. So I didn't want to super confuse you, but like that could be a digital signal where there's just more than one level at the same time, which means you can send more information. But yes, the idea of kind of, if you increase the frequency of the wave, right, like if you more pulses per second means more information being sent via the digital signal. Okay, let's have a look at this. This is one of the benefits of digital signals over analog signals is that you've got much faster rate of information exchange. You can send information at a much higher rate, data. Here's another example. Imagine this is an analog signal, right? This black line here, it's an analog signal, but it's picked up some noise. It has become very distorted. So if say you've got a mobile phone, right? Mobile phones were analog in ye olden times when I was young. So you might have a mobile phone that is sending an analog signal. That signal's got to travel a very long way. The electric signal that kind of reflects that signal would have it would just match the frequency of, say, the sound wave. So it'd have different frequencies, different amplitudes. It travels a long way, it picks up noise. Waves interact with other waves, they bounce off things. Eventually they get a bit fuzzy, right? A bit noisy. So let's say this is an analog signal, it's travelled a long way and it's got a bit noisy. How are you going to clear it up? And which one of these is correct? So this black one is the wave that has become noisy because it's travelled a long way. If you clean up the signal, which one is correct? Is it A or is it B? I'm only going to give you 10 teacher seconds for this. Is it A, the pink one, or is it B, the blue one? Which one of those is that analog signal after it's been cleaned up a bit? Oops. Five, 4, 3, 2, 1. Oh, it's a trick question. Sorry, there's absolutely no way of knowing, is there? Because analog signals cannot be easily cleaned up, right? Because there are infinite possibilities. We've got no way of knowing, looking at this, whether that's supposed to be a flat line, but that bump is a noise, or whether that's supposed to be a higher bump, or whether those two bumps are what. We don't know. We can't possibly tell. So analog signals cannot be cleaned up very easily. That's why in the 1900s, when I was growing up, if you copied a song from a cassette that had been copied from a cassette that had been copied from a cassette, it sounded really bad because then you've got to amplify the signal as well when you're playing it, so that noise gets increased even more. So yeah, very easily the signal deteriorated. That is not a problem now for you young'uns, because digital signals can certainly be cleaned up. Super easy compared to the analog signals. If we look at this and we say that it's a digital signal, the high bits are ons, right, or ones if you like, and the low bits are probably going to be offs or zeros. So pretty high chance that this signal below is this signal above, just cleaned up a bit. If you clean up a digital signal, it's called regeneration. It's a good word, isn't it? Regeneration. And digital signals, this is one of the huge benefits of digital signals that you might get asked about. They can travel a lot further. They've got a much further range because they can be easily regenerated, right? If it gets noisy, you just clean it up, regenerate it, and send it on its way again. Whereas analog signals, you can't do that. Okay. So I'm going to ask you a question about analog and digital signals that comes up a lot, but as a little warm-up, I need you to answer this question about cats, okay? Well, a student has answered this question about cats, and I want you to tell me how right they are. The question was, IGCSE question, what is the difference between these two cats? You've got two identical cats here, except they're different colours. So the student has written, cat A is brown. I want you to tell me, is the student's answer correct? How many marks have they got? And can you improve their answer? Maybe you can't improve it. Maybe you think that is the perfect answer. You've got two identical cats except they're different colours. You've been asked for the difference between them. The student has written cat A is brown. Is their answer correct? How many marks have they got? Can you improve their answer? Ten seconds now. 10 teacher seconds, so yeah, bearing absolutely no relation to real seconds. Well, is the student's answer correct? Oh, I'll give you, I feel like I'm going too fast. Just let you write something down if you're scribbling down. Okay, I've said yeah, the student's answer is correct, but they've only got 1 mark. Can you improve their answer? What has the student done wrong? Well, imagine that you can't see the cats. If someone says to you, what's the difference between the cats? And you say, cat A is brown, that's not a difference, is it? That's just a fact about a cat. You've got to compare them. So hopefully to improve the answer, you said something like cat A is brown and cat B is grey. Much debate on Facebook about whether it was orange or whether it was white. It doesn't matter as long as you've compared them, okay? So that would get 2 marks. If this was an English IGCSE, you would probably write cat A is brown, whereas cat B is grey. Physics exams, they don't care about that. But if you've written whereas, well done you. It's a good word. Okay, so bearing all that in mind, what is the difference, please? Describe the difference. Wow, it's a good job this isn't English IGCSE. Describe the difference between a digital and an analogue signal, please. Sorry. My tap is completely busted. The plumber was supposed to be coming today, but they couldn't because I'm in the kitchen, so they're coming on Friday. Okay, I think I've written, you could probably write about 6 words and get 4 marks on this IGCSE question. What I've written is this. A digital signal only has 2 values, or just an on or an off. And an analog signal is continuous. That is what you need to write in your exam if you're going to get marks for these questions. I was getting a lot of good answers about, well, various things, but this is what they want, is the difference between continuous and yeah, only 2 values, or on or off is fine. I will give you all of the past paper questions you can conceive of in the PDF in my Facebook group. Probably after this, actually, because I've already got them organised. Right, so just to finish off, we've talked quite a lot about electromagnetic waves in this waves module. We need to talk a little bit about how electromagnetic waves carry signals. You remember like radio waves, gamma rays, X-rays, microwaves? You remember they're all electromagnetic waves. The only difference between them is just higher or lower frequencies. In fact, they are continuous, aren't they? There's no like line between microwaves and radio waves. It's just humans have just decided to call them different things. So high frequency waves generally carry more information. All right, we've talked about this a bit. More pulses per second, more information sent. So high frequency waves, the ones up here, generally carry more information. So why, question, are microwaves used for mobile phone and Wi-Fi signals? Why are microwaves used? Because they are. We have talked about this before. You use a mobile phone. Microwaves are being sent from your mobile phone to a mobile phone mast and then elsewhere, and then eventually back to a different mobile phone mast and down to the person you're speaking to. Why would you use microwaves if it's the ones up here that carry the most information? Why wouldn't you use light? Why wouldn't you use light for mobile phone and Wi-Fi signals? It's very hard, this question, but I'm asking you it and not telling you it in the hope that you remember it. If I was just going to tell you everything, you'd just watch a really good YouTube video, wouldn't you? This is very hard. Someone remembered straight away what I'd said in the electromagnetic spectrum lesson, which I was really impressed by when I did this on Facebook this morning. I would not expect you to remember it. There's two reasons. Why wouldn't you use light? You might say, well, because it'd be really blinding and you'd be able to see it. Okay, then why not use ultraviolet? Well, the answer is microwaves can travel through walls. Oh, yeah. You couldn't use a light signal, could you, on your mobile phone, because it wouldn't get out of the building. Light doesn't travel through walls, do we? We know this. It doesn't travel through hands either. You'll be able to see on the other side. So you wouldn't use light. It's got to be able to travel through walls. And microwaves, generally speaking, are pretty good at travelling through walls. But radio waves are even better at travelling through walls. Why wouldn't you use radio waves instead? This is what Alice remembered on Facebook this morning that blew my mind. Microwaves can travel through walls. Why not use radio waves? It's because microwaves need shorter areals. Yeah, so you've got to remember that for your exam. The longer the wavelength, the longer the areal required to emit the wave and receive the wave. So mobile phones, if you don't want aerials, are absolutely massive to detect radio waves. Use microwaves instead. I know, humans, honestly, we're like so awful and so brilliant at the same time. All right, that puzzle aside then, why is light and infrared used to send signals down optic fibres? So you remember we've done about optic fibres sorry, I'm doing a lot of fast switching. Do you remember, just to remind you, we have looked at optical fibres in previous lessons. That is what a lot of these digital signals are being used to send signals down. You know, I mean, digital signals are sent down optic fibres. Teeny tiny little tubes, traditionally glass, or now like very good plastic that kind of behaves the same way as glass. And light or some infrared waves are, what's that called? What's happening here? Can you remember the phrase? What's happening? It's not just reflection, it's total internal reflection. We looked at how they get totally internally reflected down the little tubes, and that's how information is carried. So why do we use light for that? And some infrared? Like, why don't we use microwaves for that? Or X-rays? Last puzzle of the day. Go on, scribble something down. Really feel the pain of not knowing an answer and having to write it anyway. It's great practice for exams. Because 50% of the time, if you just write something, you will get a mark. Because it's not a total guess, is it? The first one we have already mentioned it. They've got very high frequencies, so they carry a lot of data. Well done if you got that. So in that case, why wouldn't you use something with even higher frequencies? Well, they can travel through glass. X-rays actually can't travel through glass terribly well. You can pick up glass on an X-ray because it blocks the X-rays, so that's not very useful for something that's got to travel through a glass tube. So those are the two reasons that you have to remember. light and infrared are used in fibre optic cables. So infrared, ultraviolet as well. It can get blocked by glass. So obviously, I'll show you. We have talked before about how there are some ultraviolet waves that have really high frequencies and some ultraviolet waves that have lower frequencies, right? The high frequency UV rays do get blocked by light. The ones that actually burn your skin get blocked by glass, beg your pardon. So you stand next to a glass window, you're not going to get sunburned. There's still the kind of mutation of the genes that causes, of the cells that causes cancer. Those UV rays do get through. So don't be sitting next to a glass window thinking that you're safe. But yes, some UV rays are blocked by light. So that's why. Whew. Right. Thus ends, that's quite a fast one today, wasn't it? That is all that I have to say to you about digital and analog signals. So if you're doing the Cambridge specification, I hope that helps. I'm just going to go over to my Facebook page and see if any of you have sent me any messages. And then, yeah, you might want to do some revising, for next week. Like I say, I'm not going to make it like a big, miserable exam. But I think some kind of recap lesson from the feedback suggests would be super useful. And then after next week, it's the summer holidays. So I'm off for 6 weeks, planning and parenting and frantically writing my sports magazine. And then we'll be back with energy sources. Yes, like solar panels. I think we're going to know what Donald Trump doesn't know, the difference between a windmill and a wind turbine, that kind of thing. Okay, so I'm just going to look at my Facebook page and see if anyone's left me a comment. Have I seen a Grace and Rose comment? I thought, let's see. Grace, just Grace, if you're watching. Hello. Everyone who's watching on Catch Up, hello. Oh, excellent. I'm getting some answers as well from Grace, just Grace. Let's have a look. One of them could be old or young. They can travel through glass. Dude. Very good. Grace, just Grace. Oh, and Susanna's here. Hello, Susanna. And hello, Hugo. Oh, Hugo, good to see you. Brilliant. And Susanna, fabulous. The whole crew. Those are the most relevant comments. I'm just going to check that Facebook hasn't completely arbitrarily filtered some out. No, it hasn't. Oh, yeah, it has. Duaria and Ryder. Duaria, have you noticed that I'm saying your name differently every single time now? Duaria and Ryder are here as well. Hello. All right. I'm going to go and start planning Lego Storytime for Thursday. I'll see you all very soon. Thanks for joining me. Bye.